Welcome DIKWP, 小工 aboard. Your learning journey starts now. Ever wondered if consciousness is just a glitch in the brain's code? We're diving into the DIKWP framework and the bug theory to see if we can actually predict when that spark of awareness flickers on. Forget the philosophy. Let's get neuroscientific. So, this bug idea isn't just poetic. If consciousness is a sudden neural event, where do we look? When your brain gets overloaded, trying to juggle too much, specific pathways, think prefrontal cortex, cingulate, thalamus, start firing in sync. It's like the brain's emergency broadcast system. And guess what? Right before you consciously perceive something, that P300 wave spikes. Our prediction. Pinpoint those high-load moments, measure that sync, and watch for that enhanced P300 signature. It's our first shot at catching consciousness in the act, neurologically speaking. Simple, elegant, and potentially game-changing. Now, let's map the DIKWP layers onto the actual brain hardware. Think of it like a cognitive filing cabinet. Where does the raw data become knowledge? The hippocampus is the prime suspect, damage it, and memories and semantics go poof. Then, wisdom and purpose. That's more the ventromedial prefrontal cortex territory. Mess with that, and moral reasoning and goal setting take a nosedive. The plan is clear. Target these regions, use lesion studies or precise stimulation, and see how the different DIKWP functions, knowledge retrieval, wisdom-based decisions, are affected. Can we draw a clean line between brain structure and these distinct cognitive levels? That's the challenge. Okay, individual brain regions are cool, but consciousness isn't just about isolated parts. It's about the network dynamics. How does information flow through these DIKWP stages? Enter dynamic causal modeling, or DCM. This lets us map out the causal connections, the effective connectivity between brain areas during rest versus task states. Does the path from knowledge to wisdom show specific activation patterns? And hidden Markov models? They treat brain activity as a series of discrete states. We can model semantic processing stages as transitions between these states. The ultimate test: zap a specific node with TMS, predict how the network state should shift based on our model, and see if reality matches. It's about capturing the dynamic flow of meaning. Let's pit silicon against synapses. Can an AI truly mirror the human brain's semantic journey? We set up a direct comparison. Same problem, human brain solving it while we record neural activity, and an AI like Roberta doing the same. We then dissect the AI's internal representations, layer by layer, and compare them to the brain's activity patterns linked to DIKWP stages. Early results suggest models like Roberta align surprisingly well with human semantic processing, better than others like BERT. But here's the catch: we need to be cautious. Just because AI mimics doesn't mean it understands in the same way. This isn't just about the final answer. It's about mapping the intermediate steps, the very essence of how meaning is built, both in us and in machines. Finally, let's zoom out. What about collective consciousness? Using hyperscanning, we see team members' brains synchronize during collaboration, and this interbrain sync predicts group performance better than self-reports. Could this be a nascent form of group mind? And looking ahead, imagine BCIs that don't just control devices, but decode your deep semantic intent, maybe from the default mode network, feeding it directly into an AI partner. This AI could then feed back its own processed knowledge and wisdom, creating a true semantic loop. This is the frontier, moving beyond basic interaction to a profound, shared understanding between human and machine.